Algebraic patterns part 2, quadratic. Patterns such as 0, 1, 4, 9, 16, ... do not have a constant amount added or subtracted between terms. Studying the first differences between terms, we get 1, 3, 5, 7, ... So to get from 0 to 1, we add 1. To get from 1 to 4, we add 3. To get from 4 to 9, we add 5. To get from 9 to 16, we add 7. So 1, 3, 5, and 7 is known as the first difference. The second difference, so 3 minus 1 gives us 2, and 5 minus 3 gives us 2, and likewise 7 minus 5 also gives us 2, however, is a constant. It's 2. So the second difference is 2. So the second difference is the same. Such patterns can be represented by the function f of x equals y equals x squared for x values greater or equal to 0. Functions of the form f of x equals x squared plus b create similar patterns. So the highest power of x is 2, therefore the function is quadratic. And this plus b can be any value, positive or negative. So as I said in the previous slide, functions of the form f of x equal x squared plus b create similar patterns. So we'll start off with this pattern. So 0, 1, 4, 9, 16, 25. The first difference is 1, 3, 5, 7, and 9. And the second difference is 2. So this function is called f of x, which is equal to y, which is equal to x squared. So our function is equal to x squared. So our x values are going to be 0, 1, 2, 3, 4, and 5. Subbing those into the function, so subbing them into x squared, we replace the x with 0, 1, 2, 3, 4, and 5. And our output is 0, 1, 4, 9, 16, and 25. So that's our pattern highlighted in blue. So this is f of x or our y values. So putting our x and y values together to create couples, we get 0, 0 is our first couple, 1, 1 is our second couple, 2, 4 is our third couple, then 3, 9, then 4, 16, 5, 25. So these are going to be points on the graph of the function y is equal to x squared or f of x is equal to x squared. So notice that the plus b in this case is plus 0. So there is no constant at the end. It's just y is equal to x squared or f of x is equal to x squared. So then plotting our points on a graph, we have 0, 0. So that's the point on the origin. We have 1, 1, 2, 4. We don't have space to put in 3, 9, but it would be up here. So you can see that the yellow highlighted U-shaped graph is our function. So this is the function of f of x equals x squared or y is equal to x squared. Now if we take the function x squared plus 2. So our pattern will be 2, 3, 6, 11, 18, 27. The first difference, so to get from 2 to 3 we add 1, to get from 3 to 6 we add 3, to get from 6 to 11 we add 5, and so on. And we can clearly see that the first difference is not the same, so the function is not linear. So then we have a look at the difference between the first differences. So to get from 1 to 3 we add 2, to get from 3 to 5 we add 2, to get from 5 to 7 we add 2, and so on. So since the second difference is the same, our function is quadratic. Now it's not because it's a 2, it's because it's the same. It could easily be a 3. The second difference could be a 3 or a 4 or a 5 or a 6, and it would still be quadratic. So taking x values, 0, 1, 2, 3, 4, and 5, subbing them into the function. So the function is x squared plus 2. So replacing the x with brackets and inputting 0, 1, 2, 3, 4, and 5. We get outputs of 2, 3, 6, 11, 18, and 27. So that's where our pattern comes from, highlighted in blue. So that's f of x or our y values. Then creating our couples and then plotting them on our graph. So we have the point 0, 2, 1, 3, 2, 6, and we can't fit any more into our graph, but this U-shaped graph here highlighted in yellow is the function f of x equals x squared plus 2, or y is equal to x squared plus 2. So it's basically our function y is equal to x squared. It's just been moved up 2 steps on our y-axis. Taking another pattern, so minus 3, minus 2, 1, 6, 13, 22. So the difference between the first terms is 1, 3, 5, 7, and 9. And the difference between the first difference is 2, 2, 2, and 2. So again, it's constant. So we know that it's quadratic. So this is the function f of x equals x squared minus 3. So this time the plus b is minus 3. Or y is equal to x squared minus 3. So we have our x values. We sub them into the function. We get our output, which is our pattern, highlighted in blue. We put our x values and our y values together to create our couples. And then we plot them on the graph. So we have 0, minus 3, 1, minus 2, 2, 1, and then 3, 6 would be up here. So we can't fit them all in, but highlighted in yellow is our function f of x equals x squared minus 3. So it's y is equal to x squared, but it's been moved 3 steps down. So taking another pattern, we have 2, 1, minus 2, minus 7, minus 14, minus 23. The first difference is minus 1, minus 3, minus 5, minus 7, minus 9. And the second difference is minus 2 this time. So it doesn't matter that it's a minus, it's still constant. So since the second difference is the same, it's still quadratic. So the function will be f of x equals 2 minus x squared, or you could say f of x equals minus x squared plus 2. It doesn't matter which way we arrange this. So we have our x values, 0, 1, 2, 3, 4, 5. They're our inputs. We sub into the function, replacing the x with brackets and putting 0, 1, 2, 3, 4, 5 into the brackets. Then we have our outputs, which is our pattern highlighted in blue. So that's f of x, or our y values. We put them together to form couples, and then we plot them on a graph. So we can see now that the U-shaped graph has been inverted, so it's turned upside down. So it's now actually an N-shaped graph. It's highlighted there in yellow. And that's because it's a minus x squared. So positive x squared, you get a U-shaped graph. Negative x squared, you get an N-shaped graph. So plotting the points, we have 0, 2, 1, 1, 2, minus 2, and so on. So we can't fit them all into the graph, but this is the shape it will form. So it's an N-shaped graph. So if we have a look at the 4 patterns together, we can see, so the first pattern was 0, 1, 4, 9, 16, 25, and the second difference was 2. In the next pattern, we had 2, 3, 6, 11, 18, 27, and the second difference was 2 again. That's just a coincidence. The second difference could be anything. The next pattern, we had minus 3, minus 2, 1, 6, 13, 22, and the second difference was 2. And the final pattern, we had 2, 1, minus 2, minus 7, minus 14, minus 23, and the second difference is minus 2. So it's important to note, and this will be relevant for the next video, that the second difference divided by 2 each time gives us the coefficient of x squared. So 2 divided by 2 is equal to 1. So there's an invisible 1 in front of the x squared. 2 divided by 2 is equal to 1. Again, an invisible 1 in front of the x squared. 2 divided by 2 is equal to 1. An invisible 1 in front of the x squared. And minus 2 divided by 2 is equal to minus 1. So there's an invisible minus 1 in front of the x squared again. So this is common to all quadratic patterns, that if you get the second difference and you divide by 2, you'll get the coefficient of x squared. So for example, if this second difference had been 6, 6 divided by 2 is 3, so there would have been a 3 in front of the x squared. If the second difference had been 10, 10 divided by 2 is 5, so there would have been a 5 in front of the x squared. So that's relevant for the next video, and it's relevant for quadratic patterns in general. As can be seen from the graphs, the curves are symmetrical about the line x is equal to 0, so about the y-axis. We can see that the curves are symmetrical. So the y-axis forms like a mirror line, and we've got the same shape on either side of the y-axis. Patterns in the form of f of x equal x squared plus b are u-shaped. So they're highlighted in yellow there, all the u-shaped graphs. So they're positive x squared. And patterns in the form of f of x equal b minus x squared are n-shaped. So if you have a negative x squared, you get an n-shaped graph. So that's highlighted there in yellow, the n-shaped graph.